Chapter 2 Motion in a Straight Line. Introduction. Motion is common to everything in the universe. We walk, run, and ride a bicycle. Even when we are sleeping, air moves into and out of our lungs, and blood flows into our arteries and veins. We see leaves falling from trees and water flowing down a dam. Automobiles and planes carry people from one place to another. The earth rotates once every 24 hours and revolves round the sun once in a year. The sun itself is in motion in the Milky Way, which is again moving within its local group of galaxies. Motion is change in position of an object with time. How does the position change with time? In this chapter, we shall learn how to describe motion. For this, we develop the concepts of velocity and acceleration. We shall confine ourselves to the study of motion of objects along a straight line, also known as rectilinear motion. For the case of rectilinear motion with uniform acceleration, a set of simple equations can be obtained. Finally, to understand the relative nature of motion, we introduce the concept of relative velocity. In our discussions, we shall treat the objects in motion as point objects. This approximation is valid so far as the size of the object is much smaller than the distance it moves in a reasonable duration of time. In a good number of situations in real life, the size of objects can be neglected and they can be considered as point-like objects without much error. In kinematics, we study ways to describe motion without going into the causes of motion. What causes motion described in chapter and the next chapter forms the subject matter of chapter 4. Instantaneous velocity and speed. The average velocity tells us how fast an object has been moving over a given interval time, but does not tell us how fast it moves at different instants of time during the interval. For this, we define instantaneous velocity or simple velocity v at an instant small t. The velocity at an instant is defined as the limit of the average velocity as the time interval del t becomes infinitesimally small. In other words, v is equal to limit del t to 0 del x by del t, which is equal to dx by dt, where the symbol limit del t to 0 stands for the operation of taking limit as del t to 0 of the quantity on its right. In the language of calculus, the quantity on the right-hand side of equation 2.1a is the differential coefficient of x with respect to t and is denoted by dx by dt. It is the rate of change of position with respect to time at that instant. We can use equation 2.1a for obtaining the value of velocity at an instant, either graphically or numerically. Suppose that we want to obtain graphically the value of velocity at time t is equal to 4 seconds, point P, for the motion of the car represented in figure 2.1 calculation. Let us take del t equals 2 seconds centered at t is equal to 4 seconds. Then by the definition of the average velocity, the slope of line P1, P2, figure 2.1 gives the value of average velocity over the interval 3 seconds to 5 seconds. Now we decrease the value of del t from 2 seconds to 1 second. Then line P1, P2 becomes Q1, Q2 and its slope gives the value of the average velocity over the interval 3.5 seconds to 2.5 seconds in the limit del t to 0. The line P1, P2 becomes tangent to the position time curve at the point P, and the velocity at t is equal to 4 seconds is given by the slope of the tangent at that point. It is difficult to show this process graphically, but if we use numerical method to obtain the value of velocity, the meaning of limiting process becomes clear. For the graph shown in figure 2.1, x is equal to 0.08 t cube. Table 2.1 gives the value of del x by del t, calculated from del t equal to 2.0 seconds, 1.0 seconds, 0.5 seconds and 0.1 seconds. 0.01 seconds centered at t is equal to 4 seconds. The second and third columns give the value for t1 is equal to t minus del t by 2 and t2 is equal to t plus del t by 2, and the fourth and the fifth columns give corresponding values of x, that is x t1 is equal to 0.08 t1 cube and x t2 is equal to 0.08 t2 cube. The sixth column lists the difference del x, which is equal to x t2 minus x t1, and the last column gives the ratio of del x and del t, that is the average velocity corresponding to the value of del t listed in the first column. We see from table 2.1 that as we decrease the value of del t from 2.0 seconds to 0.010 second, the value of the average velocity approaches the limiting values 3.84 meter per second, which is the value of velocity at t equals to 4 seconds. That is the value of dx by dt at t equals to 4. In this manner, we calculate value at each instant for motion of car. The graphical method for determination of the instantaneous velocity is always not a convenient method. For this, we must carefully plot the position time graph and calculate the value of average velocity as del t becomes smaller and smaller. It is easier to calculate the value of velocity at different instants if we have data of positions at different instants or exact expressions for the position as function of time. Then we calculate del x by del t from the data for decreasing the value of del t and find the limiting value as we have done in table 2.1, or use differential calculus for the given expression and calculate dx by dt at different instants as done in the following example. Note that for uniform motion, velocity is the same as the average velocity at all instants. Instantaneous speed, or simply speed, is the magnitude of velocity. For example, a velocity of plus 24.0 meter per second and a velocity of minus 24 meter per second both have an associated speed of 24 meter per second. It should be noted that though average speed over a finite interval of time is greater or equal to magnitude of average velocity, instantaneous speed at an instant is equal to the magnitude of the instantaneous velocity at that instant. Why so? Acceleration. The velocity of an object in general changes during its course of motion. How to describe this change? Should it be described as the rate of change in velocity with distance or with time? This was a problem even in Galileo's time. It was first thought that this change could be described by the rate of change of velocity with distance, but through his studies of motion of freely falling objects, the motion of objects on an inclined plane, Galileo concluded that the rate of change of velocity with time is a constant of motion for all objects in free fall. On the other hand, the change in velocity with distance is not constant. It decreases with the increasing distance of fall. This led to the concept of acceleration as the rate of change of velocity with time. The average acceleration a bar over a time interval is defined as the change of velocity divided by the time interval. A is equal to v2 minus v1 divided by t2 minus t1, which is equal to del v by del t, where v2 and v1 are the instantaneous velocities, or simply velocities at time t2 and t1. It is the average change of velocity per unit time. The SI unit of acceleration is meter per second square. On a plot of velocity versus time, the average acceleration is the slope of the straight line connecting the points corresponding to v2 t2 and v1 t1. Instantaneous acceleration is defined in the same way as the instantaneous velocity. A is equal to limit del t to 0, del v by del t, which is equal to dv by dt. Acceleration at an instant is the slope of the tangent to the vt curve at that instant. Since velocity is a quantity having both magnitude and direction, a change in the velocity may involve either or both of these factors. Acceleration therefore may result from a change in speed, magnitude, a change in direction, or changes in both. Like velocity, acceleration can also be positive or negative or zero. Position time graphs for motion with positive, negative and zero acceleration are shown in figures 2.4a, b and c respectively. Note that the graph curves upward for positive acceleration, downward for negative acceleration, and it is straight line for zero acceleration. Although acceleration can vary with time, our study in this chapter will be restricted to motion with constant acceleration. In this case, the average acceleration equals the constant value of acceleration during the interval. If the velocity of an object is v0 at t equals 0 and v at t, we have a is equal to v minus v0 by t minus 0, or v is equal to v0 plus at. Let us see how velocity time graph looks like for some simple cases. Figure 2.3 shows velocity time graph for motion with constant acceleration for the following cases. A. An object is moving in a positive direction with a positive acceleration. B. An object is moving with positive direction with negative acceleration. C. An object is moving in negative direction with negative acceleration, and D. An object is moving in positive direction till time t1 and then turns back with same negative acceleration. An interesting feature of a velocity time graph for any moving object is that the area under the curve represents the displacement over a given time interval. A general proof of this statement requires use of calculus. We can, however, see that it is true for the simple case of an object moving with constant velocity u. Its velocity time graph is shown in figure 2.4. The vt curve is a straight line parallel to the time axis, and the area under it between t equals to 0 and t equals to capital T is the area of the rectangle of height u and base t. Therefore, area is equal to u into t, or ut, which is the displacement in this time interval. How come in this case an area is equal to a distance? Think. Note the dimensions of quantities and the two coordinate axes, and you will arrive at the answer. Note that the xt, vt and at graphs shown in several figures in this chapter have sharp kinks at some points, implying that the functions are not differentiable at these points. In any realistic situation, the functions will be differentiable at all points and the graphs will be smooth. What this means physically is that acceleration and velocity cannot change values abruptly at an instant. Changes are always continuous. Kinematic equations for uniformly accelerated motions. For uniformly accelerated motions, we can derive some simple equations that relate displacement x, time taken t, initial velocity v0, final velocity v, and acceleration a. Equation 2.4 already obtained gives a relation between final and initial velocities v and v0 of an object moving with uniform acceleration a. V is equal to v0 plus at. This relation is graphically represented in figure 2.5. The area under the curve is area between instants 0 and t is equal to area of triangle ABC plus area of rectangle OSCD, which is equal to half v minus v0 t plus v0 t. As explained in the previous section, the area under VT curve represents the displacement. Therefore, the displacement x of an object is Equations 2.7a and 2.7b mean that the object has undergone displacement x with an average velocity equal to the arithmetic average of the initial and final velocities. From equation 2.4 t is equal to v minus v0 by a. Substituting this in equation 2.7, we get x is equal to vt, v plus v0 by 2 v minus v naught by a, which is equal to v square minus v naught square by 2a. V square is equal to v naught square plus 2ax. This equation can also be obtained by substituting the value of t from equation 2.4 into equation 2.6. Thus we have v is equal to v naught plus at, x is equal to v naught t plus half at square, v square is equal to v naught square plus 2ax. Connecting 5 quantities v naught, v, a, t and x, these are kinematic equations of rectilinear motion for constant acceleration. The set of equation 2.9a were obtained by assuming that at t equals to 0, the position of the particle x is 0. We can obtain more general equation if we take the position coordinate at t equals to 0 as non-zero, say x naught. Then equations 2.9a are modified, replacing x by x minus x naught to v is equal to v naught plus at, x is equal to x naught plus v naught t plus half at square. V square is equal to v naught square plus 2a x minus x naught. The advantage of this method is that it can be used for motion with non-uniform acceleration also. Now we shall use these equations for some important cases. First method. In this first method, we split the path in two paths, the upward motion A to B and the downward motion B to C, and calculate the corresponding time taken t1 and t2. Since the velocity at B is 0, we have v is equal to v naught plus at, 0 is equal to 20 minus 10 t1, or t1 is equal to 2 seconds. This is the time in going from A to B. From B, or the point of maximum height, ball falls freely under the acceleration due to gravity. The ball is moving in negative y direction. We use equation y is equal to y naught plus vt plus half at square. We have y naught is equal to 45 meter, y is equal to 0, v naught is equal to 0, a is equal to minus g equals to minus 10 meter per second square. So 0 is equal to 5 plus half minus 10 t2 square. Solving we get t2 is equal to 3 seconds. Therefore the total time taken by the ball before it hits the ground equals to t1 plus t2, which is equal to 2 plus 3 is equal to 5 seconds. Second method. The total time taken can also be calculated by noting the coordinates of initial and final positions of the ball with respect to origin chosen, and using equation y is equal to y naught plus v naught t plus half at square. Y is equal to 25 meter, y naught is equal to 25 meter, y equals to 0 meter, v naught equals to 20 meter per second, a is equal to minus 10, t is equal to 0 is equal to 25 plus 20t plus half minus 10 t square, or 5t square is minus 20t minus 25 equals to 0. Solving this quadratic equation for t, we get t equals to 5. Note that the second method is better since we do not have to worry about the path of the motion, as the motion is under constant acceleration. Example 2.4 Free fall. Discuss the motion of an object under free fall. Neglect air resistance. An object released near the surface of the earth is accelerated downward under the influence of the force of gravity. The magnitude of acceleration due to gravity is represented by g. If air resistance is neglected, the object is said to be in free fall. If the height through which the object falls is small compared to the Earth's radius g, can be taken to be constant, equal to 9.8 meter per second square. Free fall is thus the case of motion with uniform acceleration. We assume that the motion is in y direction, more correctly in minus y direction, because we choose upward direction as positive. Since the acceleration due to gravity is always downward, it is in the negative direction, and we have a equals to minus g, which is equal to minus 9.8 meter per second square. The object released from rest at y is equal to 0, therefore v naught equals to 0, and the equations of motion becomes v is equal to 0 minus gt, y is equal to minus half gt square, v square equals to minus 2 gy, These equations give the velocity and the distance traveled as function of time and also variation of velocity with distance. The variation of acceleration, velocity, distance with time have been plotted in figure 2.7 ABC. Example 2.5. Galileo's law of odd numbers. The distances traversed during equal intervals of time by a body falling from rest stand to one another in the ratio as the odd numbers beginning with unity, namely 1, 3, 5, 7, ... Let us divide the time interval of motion of an object under free fall into many equal intervals and find out the distances transverse during successive intervals of time. Since initial velocity is 0, we have y is equal to minus of gt square. Using this equation, we can calculate the position of the object after different time intervals, which are given in second columns of table 2.2. If we take minus half gt square as y0, the position coordinate after time interval t, then third column gives the position in the unit of y0. The fourth column gives the distances traversed in successive t's. We find that the distances are in simple ratio 1:3:5:7:9:11 as shown in the last column. This law was established by Galileo 1564 to 1642, who was the first to make quantitative studies of free fall. Initial velocity increases the stopping distance by a factor of 4 for the same deceleration. For the car of a particular make, the braking distance was found to be 10 meter, 20 meter, 34 meter and 50 meter, corresponding to velocities of 11, 15, 20 and 25 meter per second, which are nearly consistent with the above formula. Stopping distance is an important factor considered in setting speed limits, for example in school zones.